No, it's good. Very difficult task. All right. Good morning, everyone. My name is Maria Cherdantseva, and I'm a PhD student from the University of Western Australia. And today we'll be talking about the solubility of alkalis and also chlorine in magmatic sulfide liquids. And before I start, I would like to acknowledge my official supervisor who helped me a lot, Marco Fiorentini, and my unofficial but very helpful supervisors, Michael Anenburg and John Mavrogenes, and also Malcolm Roberts for helping me with all the analytical work. And I also would like to acknowledge SGA for financial support to come here. I really appreciate it. So a little introduction to my talk. So in magmatic sulfide systems, sulfides are often associated with potassium, sodium, and chlorine-rich minerals. And I probably must say that it doesn't have anything to do with bubbles in this case. And if you ask me, I probably will be the biggest advocate against the bubbles idea. So I'm not going to talk about it. These are just subtle rings around sulfides, which are enriched in phlogopite, amphibole, chlorine-rich apatite, chloride, all these minerals. So this association was documented worldwide, so in many deposits. So we can agree that it's common association. This is what I could find just doing like very quick 10 minutes research. I could find that many documentations of this close association. So this documentation, this association of sulfide liquid with phlogopite, with amphibole, was referred to be formed during late stage crystallization from a volatile enriched, highly fractionated intercumulus melt. So it's the last stage of crystallization from very fractionated melt. Or another explanation is that it's like a secondary phases, and you have like selective alteration around sulfides. So basically, both of these hypotheses assume that this close association is actually serendipitous. So basically, you kind of like, it can happen, cannot happen. Sulfide liquid kind of has a superpower to attract these alkalis and chlorine next to each other. Why do we have this association? So we decided to check it and decided to look at the problem from a different angles. So basically from inside out, and ask a question: what if it's not a matter of luck? What if we can dissolve some potassium, sodium, and chlorine not only in silicate melt but also in sulfide liquid? So we have decided to address this problem experimentally. So all the experiments were run at Australian National University with help of Michael Anenburg and John Mavrogenes. I used piston cylinder apparatus to run these high temperature, high pressure experiments. And we used a platinum capsule with graphite lining. I probably should point a little bit late. So platinum capsule with graphite lining, and the starting composition, we did it in layers. So we put sulfides and sulfates on the bottom and salts and sulfates of potassium and sodium on the top. So we could check the processes which are happening in the capsule. So we ran 3 experiments at conditions 1100 and 505 kilobars. So all the 3 experiments were heated up to 1100 degrees, and then they were cooled down to different temperatures. So one was a very high temperature experiment and quenched, and then we cooled down the second one to 850 degrees and quenched, and then we cooled down another one to 300 degrees and then quenched. So these are results of our experiments. So we can see that this one is a high temperature experiment, and we can see that the initial layering is disappearing now. So it's a good sign that that alkalis and chlorine do dissolve in sulfide, and they form this homogeneous aggregate. Then at medium temperature, we have like clear separation of sulfides with salt, and also clear separation of MSS and residual sulfide liquid in between. And at lower temperature, we crystallize normal sulfides again. So if you look a little bit closer at the results of experiments, so this is a high temperature experiment. We did some elemental mapping using GEOL software. It's a quantitative mapping. So you could see these blue areas in potassium, sodium, and unfortunately chlorine was not the best area for mapping it. But we can see that there are some concentrations of these elements. And also, it's important to notice that MSS is not so readily dissolving potassium and sodium in it, but still can get about 1% of sodium and about 1% of potassium and chlorine. And this interstitial liquid between some MSS, it dissolves up to 3% of potassium, 2% of 3% of sodium, 2% of potassium, and 1% of chlorine. At intermediate temperature experiment, we can see this nice blobs of MSS and this matrix, which we interpret as a residual sulfide liquid. And we can see that MSS is fully free of this potassium and chlorine, and this intermediate liquid is quite enriched in them. And then at lower temperature, we crystallize like normal magmatic sulfides, chalcopyrite, pentlandite, pyrrhotite, which are free of alkalis and chlorine. And we crystallize some alkali-rich phases such as moronskite and gerfischerite, which is not surprising because these phases are stable at lower temperatures and they're typical for high alkali systems. And then we decided to check, what if we just forced these alkalis to dissolve in sulfides because we didn't have any silicate liquid next to it? Maybe if we have silicate liquids, they will behave differently. So we also ran some experiments where we had sulfide globules in silicate melt with alkalis. And we ran two experiments, one high temperature, 1250 degrees, 5 kilobars, and one lower temperature, slowly cooled down experiment to 300 degrees. And we can see already from the first sites that there's something wrong with the sulfides at high temperature experiments. They are not like even, they have these vermicular textures in comparison with sulfides from low temperature experiments where we have not like normal typical sulfides for magmatic sulfide systems. So if we map these experiments, we can see that sulfide liquids still dissolve quite a bit of alkalis and chlorine, especially in this residual melt in between MSS. MSS is not so readily dissolving potassium and sodium. And at lower temperature, we have no potassium, sodium, or chlorine in sulfides, so they exsolve from sulfide liquid. And I'm sorry, I have to point it out, but if you look at this distribution of copper in these low temperature experiments, it looked very much like a chicken. I have to tell it, sorry. I can't unsee it anymore. So I hope I didn't lose you on the results. So just to summarize, so at high temperature, we can dissolve quite a bit of alkalis and chlorine in sulfide liquid. Then at intermediate temperature, we start exsolving them into the residual sulfides melt and outside of sulfides. And in the end, we just end up with very innocent looking sulfides. And they're so innocent that nobody ever suspected that they were dissolving any elements in them. But the smoking gun here is this close association with potassium, sodium, and chlorine-rich minerals. And also we can kind of assume that there are two paths to follow for this potassium, sodium, and chlorine when they are exsolved from sulfide liquid. They can go to these minerals bonding with silicates, or they can go into the fluid phase. And it might have some applications for the magmatic sulfide systems. I don't think there are bubbles, but I don't know how else I can show the fluid phase. So what are the applications of our founding that alkalis are dissolved in sulfide? First of all, we can explain this close association of phlogopite, amphibole, apatite with sulfides, but this is on the smaller scale, but we can actually speculate that this association can be important at different stages of magmatic processes. And here I used a schematic illustration of David Holwell, who published a paper with co-authors saying that we actually can connect deep-seated solar magmatic systems with shallow porphyry systems and form this translithospheric continuum based on the similar metallogenic signatures between these two systems. And we can argue that addition of potassium, sodium, and chlorine in sulfides can actually nicely complement this idea, because this can be a transport, can facilitate the transport of these metals between these two systems. So what I mean is, if we start from the deep, from the mantle, we can say that if we add at these temperatures potassium, sodium, and chlorine in sulfide liquid, it will probably lower the solidus of sulfide liquid. So we will need to lower temperature to melt sulfides and to mobilize metals. It will be similar to if you add water into the system. So it will be easier to mobilize metals. Then if we move a little bit up in the magma conduit, we will probably exalt sulfides again. And these sulfides will accumulate metals along with this potassium, sodium, and chlorine. And this potentially can help with transportation of this sulfide liquid, because we dissolve light elements in this heavy liquid, and it can probably move a little bit easier. And then if we finally introduce these sulfide globules into the intermediate magma chamber, and the temperature starts dropping, we can assume that this potassium, sodium, and chlorine are exsolved from sulfide liquid, because we don't document it in natural examples. And again, it can form these halos around sulfides, or can go into the fluid phase. And this fluid phase, rich of chlorine, potassium, and sodium, especially chlorine, is notoriously known to be transport agent for metals. So we can probably transport with these fluids more metals, including copper, gold, and tellurium, into the shallow systems, like porphyry systems, and then eventually form these magmatic hydrothermal deposits with potassium rich zones with lots of chlorine and metals and so on and so forth. So that's pretty much it. So the take-home message here that we do dissolve alkalis and chlorine in sulfide liquid at high temperature, but then we separate them at medium temperatures. We can decrease the solidus of sulfides with this alkalis and chlorine, and this alkalis and chlorine can potentially be important in transport of metals across the lithosphere. Thank you very much.
Thank you for a really impressive talk. I wonder if you observe such minerals like gerfischerite, moronskite, rasfumite, and other potassium-rich sulfides in your case, in your experiments.
In my experiments?
Yeah.
In my experiments, yes. In that lower temperature experiment, which I have, silica-free experiment at lower temperature, I do have gerfischerite here and moronskite.
I see. Yeah. I overlooked it. Thank you. Thank you very much.
Thanks for a really interesting talk. So there have been experiments that have been done before that have looked at fluorine and chlorine solubility and water in sulfide liquids. And so one of the applications in that case was actually to highly differentiated ore bodies, whereby through extreme amounts of crystallization, you could eventually liberate an alkali or water-rich fluid that could potentially be responsible for low sulfidation or horizons, for example, at Sudbury. So that's just a suggestion for an area where this might be applicable.
Yeah, I was thinking about it. I just didn't want to mention it because it wasn't a part of the story, but in my paper we discussed it.
Really interested in what you had to say there. Most of the laser ablation work that we do in Cardiff is based on a series of sulfide standards that I synthesized over 10 years ago. And we use a borosilicate melt and a sulfide liquid, and we quench it at 1100 degrees. My sulfide standards have about 1% sodium in them. That was a great surprise to me at the time. You know, I fished out these sulfide globules, and after a couple of days, they were coated in this white stuff that dissolved very, very easily in deionized water. And then whenever we stuck it under the SEM, you could see that they've got 1% sodium. So yeah, I totally agree with what you're saying.
Yeah, we discussed it also with Michael Anenburg, and he had old experiments where he also used some potassium, sodium, and had them in sulfides. And sulfides look very similar to what we have in our experiments. We just never thought about it, that it might be important.
Yeah.
And yeah, these samples are very, very delicate. I had to polish them every time before I go to the microprobe or SEM, because they do start to decay.
Yeah, your high temperature sulfides look very, very much like my sulfide standards.
Yeah. I'm not surprised.
So I think next we've got virtual